Then we start. Good afternoon to everybody. It is my great pleasure to introduce Professor Yuri Shprits. Yuri Shprits is a world-leading expert in understanding of the dynamics of the near-Earth space environment, which is hazardous for satellites. He has made his PhD at UCLA, where Yuri has developed the widely used physics-based model for the radiation belts. Professor Shprits was visiting professor at the Massachusetts Institute of Technology, and Yuri received many academic awards, and I just mentioned several of them. He has received an Arne Richter Award for Young Scientists from GU. Also in 2012, he received the Presidential Early Career Award for Scientists and Engineers, which was awarded by President Obama in White House. And later on, Professor Shprits won a Helmholtz Recruitment Initiative grant to lead space physics and space weather a section at GFZ Potsdam, where he has been working since then. Professor Shprits is also professor at the University of Potsdam. Yuri is involved in many satellite missions, and one of them is Prof, which is an American mission, and he's also PI of the particle detector at the Lomonosov mission. So I personally started to collaborate with Yuri with his work on particle detectors at UCLA, where I learned a lot from Yuri and his group about modeling of particle detectors. Yuri is an author of and co-author of more than 200 publications, and 12 of which are in Nature or Science journals. And I'm looking very much forward to your presentation, Yuri, which is on space weather early warning system.
Yelena, thanks so much for these kind words. So let me start sharing my screen and just say a couple of words that today the title of my talk will be Space Weather Early Warning Systems. And so for this meeting for DGG, I tried to make a presentation that actually focuses on predictive systems and early warning systems of how we can predict space weather conditions. But this presentation would be certainly relevant not just to space weather phenomena, but also in general to how we can predict geophysical phenomena in different areas, I think, of geophysics. And in particular, I will discuss in details the new advances in data simulation and machine learning and how we can use that. And maybe today we'll focus a little bit less on very exciting and very interesting and very complex science that involves this system, but we'll try to focus today a little bit more on applications of this science and also development of tools for predicting space weather. So let me start with that. This is an outline of my talk. I'll give a very short presentation, a very short introduction. Presentation is rather long. And then I will talk about various hazardous populations in space and show how we're predicting these various hazardous populations of particles. Then I will discuss our recent Horizon 2020 funded Pager project, where we're developing probabilistic predictive systems, and switch to discussion of ionosphere and density in ionosphere, and then finish with the summary. So it's quite a loaded talk, and that I'll talk about different systems, different predictive systems, so bear with me, but I'm happy to answer all the questions at the end. All right, so I'll start with the introduction. Space weather is a collective term that describes various hazardous events originating from space. And the source of space weather is the sun, and here in this movie you can see coronal mass injection, which is injection of billions of tons of plasma into interplanetary space. And then when this so-called magnetic cloud hits the Earth's magnetosphere, it can interact. Let me play that again. It can interact with the Earth's magnetosphere and cause a number of disturbances. We usually can see the visual display, beautiful visual display of auroras during geomagnetic storms, but there is also a lot of damage that such storms can do. So first of all, the disturbances in space can create disturbances on the ground in the magnetic field, and these disturbances can cause disruption of the power grids. This could be very costly and could be quite damaging. An example, in March 1989, the whole province of Canada was left without electricity for several days because of the geomagnetic storms. There is also increasing number of satellites. Satellites are providing us with television, with communications, Earth observing systems. There is now increasing number of satellites that will provide internet on the ground. Only a few years ago, I showed similar slide, and there was a number 1,000. Now it's 3,000 satellites. With increasing number was coming of autonomous vehicles, we will depend even more than now on GPS industry. Even now, the GPS industry is responsible for trucks, for boats, for ships. All of us use GPS every day, but there is increasing number of also satellites, and it's not just the US GPS system, it's GNSS system, European, Chinese, Russian. Number of satellites is growing, and dependence on the satellites is growing too. During storms, satellites can experience anomalies, and these anomalies are caused by the hazardous radiation, and I will talk about this radiation a little bit more in the next slides. But let me emphasize one thing that, as I said, recently it was 1,000, now it's 3,000. The projections are that by the end of the decade, there will be almost 60,000 satellites. There is increasing number of launches into the low Earth orbit near the Earth that will be responsible for providing internet on the ground. These satellites mostly are built very fast, and mostly they're built from off-the-shelf components. So I think we will see even more dependence on space weather than we've seen in the past. The first example of that was recent anomaly of Starlink satellites, where I think 49 out of 53 re-entered right after launch. So here I will talk focus more on the effects of radiation on the satellites. But let me first start with a little introduction of what are these populations and what is the subject of our talk. So first of all, we are protected from the space radiation by our magnetosphere. Magnetosphere is the magnetic cavity in the solar wind, where the magnetic field of the Earth dominates over the magnetic field of the sun. Even though we call it cavity, this cavity is not actually empty. Particles from the sun originating from the sun, and also some of the particles from distant galaxies can penetrate this cavity, this protective shielding, and even occasionally they get accelerated inside of the magnetosphere. So there are a number of populations of different particles, mostly electrons and protons, though there are also what we call heavy ions, even though I wouldn't call necessarily oxygen a heavy ion or helium, but we call them heavy ions because they're heavy compared to protons that populate this region of space, very important region of space where our satellites operate. So there are a number of different populations, and usually we classify them by energy, by the energy of those particles, because the energy of those particles determines the physics and evolution and dynamics of this particle populations. So I will start with the lowest energy and then go on to maybe even more interesting and exciting higher energy particles. So first of all, plasma sphere. It's lowest in energy. We call this plasma cold. Its temperature is around 1 eV. This plasma originates from ionosphere, and basically plasma sphere is a bubble of cold plasma that correlates together with the Earth. It's of course also organized by the magnetic field. That's why on this illustration, where plasma sphere is depicted as green, it's tilted, same as the Earth's magnetic field. So it's very cold. Energy is about 1 eV. At the same time, if we convert these temperatures into Kelvin, that's 10,000 Kelvin. So that sounds pretty hot to me. But I will also present these numbers of temperatures in Kelvin for other populations, though physically they don't make too much sense because the higher energy wouldn't be in equilibrium, and temperatures for them don't really make physical sense that much, or in thermodynamics doesn't work for them because they are not in a thermodynamic equilibrium. So plasma sphere is a cold bubble of plasma, and I will show how we're modeling that with machine learning tools and how machine learning can help us describe this population. It's important to know because this cold plasma determines charging on the surface of spacecraft, and also cold plasma can contribute to the delays of the GNSS signals. So the next in energy population is called the ring current. It's called ring current because it's actually almost looks like a ring, even though it's not completely symmetric, and it's also a current. This energy particles of about tens of keV, so already much hotter than cold plasma sphere. They're more energetic and they start drifting around the Earth. And this drift around the Earth in the electric and magnetic field creates a current. We can see the effects of this current on the ground because it creates a negative magnetic field. And also intensifications in ring current or sudden disturbances can produce changes in the magnetic field, which can be damaging to terrestrial power grids. Another important effect of ring current, as I said, is surface charging on spacecraft. And so when the surface of spacecraft is charged, then it can discharge and damage sensitive components on a satellite. So we'll discuss modeling of the ring current, which is also very challenging. We have physics-based models, but they're not accurate enough. And so I will talk about how we blend them together with some data simulation. The next higher in energy population are radiation belts. These are arguably the most exciting and interesting population. That was the first discovery of the space age, that space was radioactive, and we still don't completely understand the dynamics of these particles, and still learning new and exciting things about these populations. Here, a number of satellites operate, and these particles are so energetic that they can penetrate satellite protective shielding, and they will be deposited in the sensitive electronic components, and they can significantly damage spacecraft. These are also scientifically very interesting particles because they're very energetic. Their energies are from half an MeV to 10 MeV. So their kinetic energy exceeds their rest mass, can exceed their rest mass by a factor of 10 when they become so-called ultra-relativistic particles. So these are going very, very close to the speed of light. So let me then start showing you how we model these populations, and at the end I will also switch to ionosphere and discuss ionospheric hazards and how we model them with machine learning. So once again, this is a plasma sphere bubble of cold plasma. First we tried only recently we realized how dynamic is this population. These are images from image satellite, has the same name, and they outline manually. Here's an outline of the plasmasphere, boundary of the plasmasphere, this cold bubble of plasma. So it turns out that this population is very dynamic, shows lots of different shapes that have their names. We call them plumes, shoulders. There are different features in the plasmasphere. Important things to note that the variables here is magnetic local time. This is time with respect to magnetic field, and L shell is the distance from the center of the Earth to the given point in the equatorial plane. So we have only very few observations. We had image spacecraft that operated for a few years and provided us global images, like I showed before, where we can infer the boundary of the plasmasphere. But most of the information comes from individual satellites. And here's an example of an orbit. They provide actual densities, but these densities are only point measurements, so they are not global. And in that sense, they are difficult to interpret and see the global picture and understand too. So in this case, from this point measurements of a single spacecraft going through this orbit, we created a machine learning model. So we asked machine learning neural network to learn from the single measurements, point measurements in space, given at different points in space and time. And we asked the machine learning to create a global model. We gave it 4 years of the input. We gave parameters of the solar wind, geomagnetic indices, and location, and asked to provide a global output in the equatorial plane of the shape of the, and actually densities in every point. So something like that, right? So, and then we tried to see what are the optimal parameters. There's so-called feature selection that we've done. And we looked, it turned out that we need to provide not just the parameters themselves, but also history, time history of these parameters. And then we focused more on geomagnetic indices because it turned out that solar wind data sometimes gappy, sometimes difficult to infer information, work best with indices alone, and looking for 48 hours in the past. So here's the result of the model, which was trained on data collected after 2012. But then here we're validating that on the global images from image spacecraft in 2001. So the left panel shows the image picture, and that's inferred from, it's in direct measurements, it's inferred from recombination of helium ions, but sort of shows us at least the shape of the plasmasphere. And then on the right, we see the results of the machine learning model, and we can see that it approximately follows a similar shape that we predicted for this particular time and this particular storm. So let me show you a more detailed validation. Here again, points are manually inferred from image satellite data points of the plasmasphere, and then you will see evolution of the plasmasphere, global evolution that is predicted by the machine learning model. So it's quite interesting that we were able, first of all, machine learning model was able from single point measurements to understand the global structure of this 2D region of the plasmasphere. But not only that, was also able to accurately predict all these complex features, such as plumes and shoulders and gradients and so on and so forth. We tried to validate it also on the data from an individual spacecraft. Let me just say, before I move to that, another interesting aspect of machine learning that we need to take into account, that it works really well for the data that it has seen, but once we have extreme events, which are often most interesting to us, or most interesting in other areas of geophysics, like strong earthquakes, then the models can fail. So here's an example of very strong storm, and we modeled in the center. You can see physics-based model. That's our model based on physics, on advection and this complex drifts. On the right is a machine learning model. And so you can see that once it predicts things fine, but once we get to the storm, and that's drop in DST index, the machine learning model starts going nuts, predicting something absolutely unrealistic and unreasonable. So here we could combine this this model that predicts things quite right during more quiet times, and combine it with physics-based model that actually makes reasonable predictions during storms, and we now blend them by means of data simulation, and that's the illustration on the left. So once again, in the middle is the physics-based model that predicts reasonable evolution, but not as accurate as machine learning model. But it can be blended together with a neural network during extreme events, and then could provide much better output. All right, so we're moving on in energy to higher energy, and this is ring current. This population is also very dynamic. It can change on the scale of minutes by several orders of magnitude. That does not happen to oceans or atmospheres, but can easily happen in space. So modeling of this particle populations also create significant challenges. Here's an example of a model. This is basically an advective model. In space physics, we call it convection by analogy to atmospheric circulation. But in reality, this is more. This is actually advection. The particles are brought in by drifting in the electric and magnetic field. And because they're energetic, this drift takes them around the Earth. And here I'm showing 3 different populations of 1 keV particle, 6 keV, and 30 keV. These are typical energies of the ring current electrons. So these simulations could be rather inaccurate because of the complexity of the physics involved in there. There are wave-particle interactions, advections. You need to know magnetic field very accurately, and electric field also very accurately. And most of these parameters cannot be known ahead of time. So here, adding data simulation that can blend observations with the physics-based model in an optimal way is absolutely critical. So it's also important to validate our data simulative and physics approaches. So in a recent study, we tried to compare what we can produce with a Japanese Arasi spacecraft, and we were lucky because NASA's spacecraft Van Allen probes overlapped with the Japanese JAXA spacecraft Arasi, and so we were able to take measurements from Arasi spacecraft, assimilate them into our model, and that's the top panel here, and I'll explain what it is here. And then through this assimilated state, we were able to fly a virtual spacecraft and compare this virtual spacecraft to the observations on NASA's satellite. So here you can see we're looking from above. The black side is the night side of the Earth, the black half circle, and white is the day side. So this little circle is the Earth. And then we're seeing, looking from above, from the North Pole, we're seeing how particles are injected and then are rotating around the Earth. So on the left side, the format of this plot is the following. X-axis is time, Y-axis is L that I introduced before, which is basically the radial distance from the Earth measured in Earth radii. So here you can see comparison of data simulation, and we've flown virtual NASA spacecraft through it. And the second panel shows the actual measurements from NASA's Benaline probe spacecraft. So we're very impressed. In spite of this, a lot of uncertainties and variations by orders of magnitude. Note that here's a color bar is a log of density of these electrons. We can reproduce the general evolution by using data assimilation with physics-based model. All right, so now we're shifting to the highest energy populations. These are the most energetic, to me, I would say the most exciting, how particles can be accelerated to such high energies. And they are actually accelerated inside of the Earth's magnetosphere. Here, an illustration shows magnetic field lines originating from core mantle boundary. And these blue ribbons are magnetic field lines that stretch into space. They are compressed on the day side, that would be to the left in this case, and stretched on the night side. They could be stretched up to 200 Earth radii, and on the day side, the magnetosphere goes only to approximately 10 Earth radii. But it doesn't only protect us from the radiation, it also can trap this most energetic particles in the Earth's magnetosphere. And so we've made a lot of advances in understanding where these particles come from and how they get to be accelerated to such high energies. And to summarize this, I think the main part of this discovery, though they were quantitative, and we were able then to quantify, was that it's that particles are strongly affected by plasma waves that are in the Earth's magnetosphere. And here is an illustration of different plasma waves. We're looking from the top, but we found lots of interesting and exciting things. I would say main discoveries were that particles can be heated locally inside of the magnetosphere, that they're not brought from outside, that waves provide energy for these particles and accelerate them to such high energies. But as I said before, today I want to focus on predictive systems, on machine learning and data assimilation. And I'll show you an example of the here a data assimilative system that already works at GFC Potsdam and functions in real time and makes predictions that stakeholders, satellite operators, companies can use and look into the state of the space environment using data assimilation. So here, blue lines are again magnetic field, and you can see Earth rotating and magnetic field lines rotating with them. And in this particular example, we're looking at RBSP A and B. These are abbreviations for radiation belt storm probes. These are Benaline probes spacecraft, NASA's spacecraft, and then GOES satellites that are orbiting in the geosynchronous orbit. These are NOAA's meteorological satellites. And we're working on including a number of other spacecraft into the system as well. So you can see trajectories of different satellites. On the bottom, you see our reconstruction that these are donut-shaped region, outer zone electrons of this very high radiation. Then on the right, you can see the measurements, how they are mapped. And this is one particular energy and one particular energy, and you can see how here measurements from all the spacecraft are mapped onto time and radial distance. This is distance, once again, y-axis is distance in Earth radii, x-axis is time, and color-coded are fluxes of particles. So let's say Benaline probes goes in and out of the belts, and you can see here that it crosses L shells, so crosses different distances. And geosynchronous spacecraft, they're at a fixed distance in space, but they also have some variation in the magnetic coordinates. And this is their line on top. So all this data is being collected in real time and then blended according to underlying errors of each of these measurements together with a physics-based model that predicts the evolution of these particles based on wave-particle interactions, quasi-linear theory, acceleration of particles, loss of these particles into the atmosphere, and transport of these particles at the same time. And so same as meteorological models that predict terrestrial weather and blend forecasts of meteorological models together with real-time measurements. Here we're blending real-time measurements with their physics-based model. Here is a dashed line, and you can see the data stops here. So this is the current moment. From this data, we're issuing a forecast into the future, and your forecast is as accurate as the initial conditions that are given to the code. So we can also improve nowcast and forecast up to a couple of days. All right, so we have a recently funded Horizon 2020 project, which is abbreviated as PAGER. And in this project, we actually try to look beyond individual predictions of these areas, though we combine them as well. But we wanted to provide longer-term forecast. Moreover, same as in meteorology, you sometimes get predictions that there is 40% chance of rain or 60% of chance of rain, rather than telling you it's going to rain or not going to rain. So we tried to do the same with a probabilistic forecast of conditions in space. And so we want to have a probabilistic forecast, and we wanted to provide a forecast with sufficient lead time so that stakeholders can, let's say, move satellites into protective mode or reschedule maneuvers or software updates. So to do that, we need to start predictions all the way from the sun, and then track those disturbances from the sun to the Earth's magnetosphere. And we started with we collected different groups from around the world with leading state-of-the-art models of the environment, space environment, and attempt to couple them. But moreover, we tried to perform ensemble simulations throughout this this whole chain of events, so that we can actually provide probabilities to stakeholders, so that they could decide if it's worth reacting to those predictions, or maybe the chances are too low and it's easier for them not to reschedule maneuvers or updates. So we started with the University of Michigan code that predicts coronal mass ejections, how they leave their solar atmosphere and how they arrive at 20 solar radii. Then we run the code that was developed at the University of Warwick, and here you're seeing slices of global heliosphere. So little circle in the center is our sun, and we're looking at the heliosphere, and there is another circle on the right, and that's our Earth. So we track these disturbances in 3D, how they propagate, and I'll show you then later movies of how we're actually doing this. Then this is passed to models of plasma waves that are developed by IIP in Prague. We're also predicting global state of the magnetosphere with the global MHD code, also from the University of Michigan. And then we move to what we already discussed, to the codes that I introduced before: radiation belts, ring current, and machine learning based plasmasphere, and also global geomagnetic KP index. I decided to skip that due to lack of time. That's also machine learning based model. So it's important for various stakeholders, for TC predictions, for understanding ground induced currents, but mostly in this project we focus on satellites. And so we actually, a company in France is modeling exactly charging on spacecraft, can tell which spacecraft will be in danger, which spacecraft will not be in danger. So we already, we're in the second year of this project. We already have some predictive systems, and I just want to show here an example of a CME modeled with this predictive chain, where we start from the sun. Then you can see the disturbance propagating in space, heating the Earth, and then here are predictions of the solar wind conditions. These four panels, this density, velocity, temperature, and magnetic field, are compared to the measurements and so-called L1 point. It's a Lagrange point in front of the Earth. So basically measurements of what is arriving at the Earth. And then of course, this system will be connected to the various other predictions that I described before. And here's our website where actually most of these modules are already working, but we're now working on organizing that with deploying containers where each model is a container and orchestrating that with a so-called Kubernetes cluster, where if one container fails, it can be relaunched again as a copy of this container predictive system. All right, so I'm moving on to the last part of my presentation. And here I will talk about ionosphere and ionospheric modeling. We have a recent project together with DLR Jena and DLR in Neue Shprits, New Institute for Solar Terrestrial Physics, where we are modeling plasma density, but from different perspective, without using physics-based model, but only by using the machine learning-based approach. This approach allows us to model this complex system that is actually very important for GPS, GNSS navigation, important for a lot of different applications. Density is also critical for propagating systems. I suppose it is also important for estimating geophysical properties with GNSS satellites. Here's an example of how total electron content, total number of electrons, is varying in space and time, and also an example of how the signal can be disturbed by differences in plasma density of the GPS and can cause divergence of the signal. So ionosphere is the ionized upper part of the atmosphere, and ionosphere, the ionization of particles is produced by the solar EUV radiation and also by precipitating particles. These are particles, same particles that I discussed before, but they can also be lost to the atmosphere and produce ionization in the atmosphere. Usually these are ring current type energies. So the methodology in this was to combine all different measurements from various different sources, in situ measurements, line of sight measurements. There is really increasing huge amount of measurements in space, and hopefully all the thousands of satellites among that I showed before, some of them will probably also carry measurements of electron content. And so we combine them by means of machine learning, data management, and then at the end, the machine learning model, same as the model of the plasma sphere that I showed before, should provide us a global model where we would see densities as a function of height and geographic conditions. So we already have done intercalibration of different satellites. It's really important to make sure that all these measurements are the same and are intercalibrated with each other, that we use that we can then give that to the machine learning model that doesn't understand which measurement comes from which satellite and which one to trust. And then once they're intercalibrated, we can then give that to the machinery of the global global model. So here's an example, and we're looking at the geographic latitude. So here's the density as a function of height on the left plot. Here's the density as a function of time. And here's density at a fixed height, and you can see how that evolves in time. But in days of the year, so these are annual variations that you can see on the right plot versus daily variations that are in the center plot. But it's quite interesting. We see a lot of features. We're doing now validation of this, and it's very impressive what we the results that we obtain with the machine learning model. Here's one example where we compare it to international reference ionosphere. This model has been developed for many years, and it looks like neural network model is at least performing the same way, or actually here outperforming IRI model. All right, so here's the summary, and I know this was a lot of information of different geophysical space phenomena, where we looked at different tools of, but I want to introduce different tools, especially machine learning and data assimilation, that allows us to make much better predictions of the space environment. Space weather is important, and we're only now understanding of how much we depend on satellites, and also how much we depend on power grids and power in our homes. And power grids and satellites are vulnerable to space weather conditions. In the last few decades, over the space age, we haven't seen very strong geomagnetic storms, but we know that they could get much stronger. 100 years ago, there was a so-called Carrington event that was much stronger than what we've seen so far. And we need to be prepared for that. Usually, this is German Geophysical Society, but usually people think that Germany is immune to such disturbances because we're not that much north. But in reality, if the storms get very strong, then the center of action, the auroral oval, will be somewhere at our latitude. So we may be in danger as well. And we need to better model and understand all these dangers too. Satellites that we depend on, and for life on the ground. There's a very rapidly increasing number of satellites. Apparently, number of satellites is increasing faster than Moore's law, and so the satellites are vulnerable to space weather. And now is the time to better predict space weather. And these are goals of our Horizon 2020 project, in which we are performing a probabilistic forecast, and we're also utilizing different sources of data and blending this data with our forecasts by means of data assimilation, in particular by means of Kalman filtering. There is an increasing number of machine learning models and machine learning tools that can often show remarkable performance, I would say. Machine learning is capable of learning from single point measurements and reconstruct the global picture of plasmasphere, of ionosphere. And these are very impressive tools that I think will allow us to produce much better early warning systems and predictive systems. We have also recently demonstrated the applicability of these tools by blending a lot of data, 19 years of measurements from different spacecraft, that also allow us to reconstruct complex structures in the ionosphere in terms of longitude, latitude, altitude, and time. So I think these are really exciting tools, and it's very timely for us to develop all these tools when there is such an increase in the information, such an increase in satellites and data that comes from the satellites. And I'll stop on that.
Yuri, thank you very much for sharing your impressive results and very educating presentation. Questions, please, from the audience. You can use chat or raise a hand. Maybe I can start with the questions. You have shown a project Pager. How long does it take to run all the chain of the models in order to predict space weather for certain time?
Yeah. So that's a good question. We do have a lot of things that here we're trying not just to. Am I still sharing my screen?
No, that's bug again because Mr. Vorbringer muted himself, and spatial chat doesn't work.
right?
Okay. Can I help with doing something? Shall I?
Does any one of you have an unshare button at the?
Yes, I have. So I press the button.
Yes, please.
Okay. Now the button is called Leave Stage.
Does anyone have the button now?
It says only one screen share allowed. I mean, I can probably explain that without showing slides too. So, so the most difficult, it turns out that the most difficult thing to predict is actually how CMEs are being transported to 20 solar radii. This is the most time-consuming simulation that cannot be even done in real time. The rest turns out to be not that difficult. Another difficulty maybe is in modeling global magnetosphere, but we don't need to do that because we can just combine solar wind with directly with input for radiation belts and machine learning models. So all machine learning models are very fast. That's not a problem at all. Ring current starts becoming slower, and then we have bigger machines that do that with hundreds of CPUs. And so far, that seems to be reasonable and realistic. So far, we can run them. The next level challenge will be when we start doing the ensemble forecast, because then we need to start running in parallel hundreds of those simulations. But so far, it looks like we can do that. The only bottleneck that we had was simulations close to the sun, but to overcome that, we pre-calculated 100 different coronal mass injections. And so we're now testing how we can just insert this 100 coronal mass injections from the library and start with them. So find the one that's closest, originate then from the solar disk where it's observed, and then now we're testing and trying to see how well that would work and how well we would be able to predict the final conditions. We probably wouldn't be able to predict that accurate, but the idea of this project that we will not be just giving one definitive prediction, but instead that we will be doing ensemble predictions. So we will perturb the properties of the CME, will perturb its location and where it's being launched. And then we will hopefully get the number of ensembles, and these ensembles will cover. So we've done first test, and so far it looks very promising, but there is a lot more work to do with the ensemble forecast, and then seeing how this ensemble propagates into ensemble of plasmaspheric conditions, ring current conditions, and radiation belt conditions.
With which delay you could you aim to predict space weather?
So we can actually give quite a good warning, because it takes during strong storms it takes about a day. For sometimes it's quieter conditions, then it's 2 days. For a day for this disturbance to propagate from the sun to the earth. So that's 1 day lead time. But then for radiation belts, we can get also a couple of days, because it takes another 2 days for waves to speed up these particles to relativistic energies. So the total lead time could be approximately 3 days, which is much better than, you know, when you are looking at what actually already happened. So then 3 days warning is something that stakeholders can already start dealing with.
Thank you. Thomas?
I apologize for the distraction I caused by pressing my mute button. So thank you for the presentation, which really opened my eyes for a field which is not in my field of expertise. So maybe my question is a kind of question of an ignorant. I understood that you've used two different approaches of modeling. One is physics-based with data assimilation, the other one is machine learning. And my understanding is that I understood is that machine learning approaches do quite well in comparison to the physics-based modeling scheme. So my understanding would be that this might be because the physics-based models are not detailed enough. They do not capture all the complexity of the problem. So my first question is this understanding correct? Have I got this correct? And if yes, could we in turn learn from the machine learning approach at which point the physics-based models are not accurate enough or where they could be improved?
Yeah, I think thanks so much for this question. I think it's a very, very good question. In some cases, we cannot tell which one is better because we haven't done accurately this comparison. In one case of the plasma sphere, we actually have. So there we and this all these areas. So I discussed plasma sphere, rain current, radiation belts. All of them are very different. Sometimes we know physics better. Sometimes we understand physics well, but then no matter how much physics you understand, there's still parameterizations that come in. So in atmosphere, that would be subgrid parameterizations that are smaller than the grid size. In our case, this would be parameterizations of different plasma waves that are used for our model to accelerate particles. So even if the understanding is detailed, you still have errors in the model. And these errors, we're trying to compensate by using all available observations and correcting these models. But which one is more accurate, machine learning or physics-based? I don't think this question is still open.
Okay.
My guess is that in many cases, when the observations are available in real time, then physics-based with data assimilation will beat machine learning. But in general, it looks like machine learning can beat physics-based models, at least for the plasma sphere, where we didn't do any data assimilation because there's not much data available. So there it's pure machine learning versus physics-based. Machine learning is doing much better, but it has one, there's one difficulty with it, that it's doing really well over time, except for most interesting events such as storms. And so then we need to, what we did, we blended our machine learning predictions with our physics-based predictions by means of, again, Kalman filtering. So they're weighted. And so machine learning provides very good, accurate initial condition for the physics-based model, then runs mostly over storm. And this way we can get the best of both types of the approach. But this is something really important for us to understand. Which one can work better? But you also asked what physics can we learn from them? Some people say that this is not physics because these are just black boxes. In reality, we can understand a lot of physics because I showed a little bit, I didn't have time, of feature selection. We could see what are the conditions that determine the evolution of the plasma sphere. What are the combinations, let's say, of the solar wind parameters, velocity times density, temperature? What are the things that are changing? And machine learning can provide us this information, can determine what are the critical conditions for, what are the critical parameters for making predictions or combinations of these parameters. What are the delay times? So I showed this 48 hours. That means that something in the magnetosphere remembers the input from the solar wind for the last 48 hours. So there's a lot of physics that we can learn from there too, but also predictive systems, of course. Too.
Thank you very much.
Thank you for this question.
Any other questions?
There was, oh yeah, okay.
Yeah, thank you. Well, I have a question which goes almost into the same direction, which is more general, not on the specific questions on the plasma sphere, etc., as I'm in marine technology. And we have a similar problem with extreme events like freak waves or monster waves, which have been ignored in models, and even meteorologists denied and said these were seafarer stories, etc., Seemannsgarn in German. And just in recent time, we know that these extreme events really happen. They are very difficult to predict. And because, well, the physical side and the equations we have become, well, not singular, but at least the confidentiality and error bars are increasing. So this is one point, and the models are always a little bit smoothing away these things. Now my question goes, what do we do? Because we have this phenomena, we have a society which is more and more anxiety driven, and we have the IPCC, which is frightening all our future based on models. What shall we do as geophysicists are basically modelers and producing nice computer pictures and movies, but is this true, and do we need some more, well, not artificial intelligence, but kind of human intelligence? That means holistic knowledge on sound knowledge and literacy on things, and how can we cope and even predict the failure of similar models? How shall we accompany policy and decision-making processes who are also frightened by the outcome of these models, which are fancy in press releases? Thank you.
Thank you for this question. Yes, I agree with you. There's no substitute for the understanding of physics, because only that allows us to look at the extreme events. There are some things that and machine learning models that learn from the past, they have hard time predicting events that are rare in the data sets. But there are still ways how we can cope with this. So one thing that we tried was taking extreme events, more disturbed events, and then multiplying them for the training. That way the model starts learning about their existence and can understand the conditions for them, because usually they occur for, at least for us, for particular conditions. Let's say when the solar wind speed was very high. Another way that we're exploring of looking at these extreme events is by running the model and then training the machine learning on the outputs of the model. So then we'll get one machine learning model that combines our physics insight in that together with a lot of data that was collected before. There's another approach that we haven't tried, but is also very promising for many fields, maybe not for everything, is physics-informed machine learning tools. So here you give the machine learning constraints, and this is usually physical equation. Let's say that divergence of magnetic field should be 0 because there are no monopoles, or that you give it even equation of advection or some physical knowledge from inside, and create this as a constraint for training, and that could also improve machine learning tools. So I guess the answer is that we should be aware of limitations of this approach. And we certainly, it's not a substitute to the physics-based models, but there are still ways of how we can try to use advantages of this methodology for creating better predictive systems.
There was also a question in the chat from Heiner Igel. He asked whether there are good estimates what the maximum magnitude of these events could be, for example, in terms of multiples of 98 storm intensity.
Yes, there are estimates. We could, there are estimates of what the disturbances on the ground were, though they are very contradictory. There are also estimates. We know how fast was the solar wind speed because Richard Carrington observed the coronal mass ejections, and then he observed the disturbances on the ground. So we know how strong, how fast the solar wind speed was for the Carrington event. But then I think, so we have some estimates. We have also seen recently, I think in 2012, there was a very strong coronal mass ejection that didn't hit the Earth. But if it would hit the Earth, it's possible that it would have been a Carrington event. So the University of Michigan that I mentioned before that runs this code, they run investigations on this. But it's also then becomes a lot of interesting physics after that, because this is an extreme event. So in extreme events, the outcome is not cannot be predicted right away. So it's not the same dependencies. It's really non-linear. Really, systems respond differently. For example, I think that we may not see a big increase in ring current because magnetopoles will be compressed and a lot of particles will be just lost from the system because there will be not much of a magnetosphere left, so to say. So we need to study these extreme events and in particular study how different systems are coupled to each other. That would probably be the same for oceanography, that you would have maybe potentially different coupling to the atmosphere. So extreme events is a very interesting subject, and we certainly need to focus on understanding physics of extreme events. Here I was mostly talking about the routine predictions of day-to-day events, which is another task, but also an important task because operators want to know, what's going to be tomorrow. But I would say it's a slightly different question, slightly different task to understand what are the effects of extreme events and what is the physics that will be in place in case of an extreme event.
Thank you very much, Yuri. I think we are unfortunately run out of time. Thank you very much again for this very exciting talk, and thank you very much for the questions to our audience. And people who would like to ask questions, they may chat maybe with Yuri in cafe. I'm sure there are more questions that we could handle during this session. So
thanks for inviting me and thanks for the questions.